Yeah, so thank you first of all, folks for joining in. And Kasam, again, good to be here. So I'm Subhasish. I am a senior technical program manager, Azure OpenAI service. So I'm part of what we call the customer experience engineering team, which is part of the Azure AI platform engineering team at Microsoft. And we will cover today basically, talk about what SLMs are, what's the different use cases, and specifically look at a Microsoft research product. This is very important to understand, is what we call the Phi-3 family of models. And recently you had the 3.5, right? So let's kind of dig, deep. So agenda again, we'll try and take a look at what SLMs are, use cases. 3, we will take a look at, and also 3.5. I updated the slide with all the information, and then some basic understanding of the technical specifications, because there are a lot of, let's say, minute functional differences in how the pre-training happens, the post-training optimizations happen amongst the different models. Those are very important to know for use cases. But in our limited time, we'll try and cover whatever is there, right? And then, of course, performance at a very high level architecture. And then we'll try and save more time actually for the demos, because the concepts are very clear when you do hands-on using Python stuff, right? So some basic, housekeeping stuff before we kind of deep dive into the SLMs is quick look at what the vision of generative AI is. So in summary, you may kind of think of this as the essence of AI is that when the first, our founding fathers kind of thought of or dreamt of was a very simple vision. That is, can the computers someday, understand us instead of, us making all the effort that we currently do, basically trying to build complex algorithms, etc., right? Mathematical models, understanding them. So this remains still the underlying force for all the research, the mathematics, the statistics, the complex, neural network, and the right now the recent post 2017, the transformer models, and the dozens of variants of the transformer models that we have, right? All of these you see the different STT models, the different NLP models are basically nothing but the variants of the transformer models, right? So leading up to what we have, what we known as the generative AI today. So this is the founding vision, which still holds good. A quick overview of the Azure AI breadth of LLMs available to you, right? And SLMs are a part of the entire breadth of offerings, you may say. So with Azure AI, again, we bring a comprehensive selection of frontier and open models, which kind of enables you and as a customer to kind of choose these models right from the screen as you see. And so they are classified into different categories, right? Databricks, Hugging Face, Meta, Microsoft Research, Mistral AI. In fact, the team which I belong to has actively worked with multiple of these vendors and OEMs and let's say LLM providers to onboard these to Azure AI. This is also one of the things that my team actively works on or participates in, right? And here you see these small language models also kind of highlighted. You had the 1, the 2, the 3, and now the most recent 3.5. So in case the takeaway from this slide is, in case you haven't checked out the entire AI model catalog, I suggest you do it this, after this webinar. So this is important. Now coming to specifically SLMs, we're going to talk about SLM. So technically, what exactly is an SLM? If someone asks you, right? I have an understanding of what a language model is. I know what an LLM is. So what exactly is an SLM? If you can articulate in, let's say, a very brief, if someone asks you, right? So basically, for us, it's a compact AI model, which basically has a smaller, you may think of it as a neural network, lesser number of parameters, less training data compared to a larger language model, LLM. And this is very important to remember. It's not just the size. You have to talk about it from the lesser number of neural network layers, lesser number of parameters, and also lesser training data. And we will take a look at it when we look at the slopes of the gradients of how the SLMs perform with LLMs in one of the images that we have later on. And SLMs so basically provide 4 key values. I mean, why are they right now important? They're one of the hottest areas of research if someone wants to get into, right? And we are seeing massive traction, of course, in the LLMs and the frontier models and the base foundation model, but also in SLMs as well. So first is SLMs are massively cost effective in terms of cost incurred by engineering teams to train and maintain them, not just the first time, but then the continuous redeployment, right? And I'm talking about both the base SLMs, if someone takes a Phi-3 kind of a model, or you're building maybe a custom model based on that, right? It's cost effective for both compared to building a multi-billion or a trillion parameter model. Second, much lesser compute required, which means you can deploy decent size GPUs. Now, compared to SLMs, if you, let's say, talk about a traditional multi-billion parameter or even a trillion parameter LLM, they're very power hungry, they're very resource intensive. But on the other hand, if you contrast, SLMs require much lesser power, lesser resources, because the pool of the fundamental reason is because the pool of data from which they draw their intelligence, which is neural networks, the self-attention layers, right, is much smaller. So if you build task specific, SLMs, that's the objective, right? You will have higher deployment flexibility, and you will have at a much lower cost. Again, the first point. Then third, owing to smaller size, you have better opportunities to run these very smaller, let's say, but highly optimized language models on smartphones, on mobile devices, on edge devices, correct? All kind of devices that operate at an edge and connected to the cloud, which in turn means it also allows you to keep data, within the device, which provides you the ability to have very low latency or ultra low latency kind of, environments and better privacy as well. And finally, coupled with the right strategy, if you utilize all of these, cost-effective deployment and correct low latency environments, so you can then design specifically SLMs which kind of target individual well-defined tasks. Like, for example, it could be knowledge retrieval from a repository or tech support, which we have seen can tend to outperform much larger models in effect of all these three. They are much more cost-effective, deployment flexibility, and low latency. So this is some of the points. Now, there are dozens of use cases. At a very high level, you need to keep in mind there are two basically categories of buckets in which you can put them. Into what's them. This is, again, please understand, this is not an exhaustive list. You can have more, use cases where you can work. But at a very high level, two buckets to remember. First is any kind of environment which is resource constrained in nature. What does this mean? So this basically buckets all of the use cases around offline environments like edge devices, specific hardware requirements, or mobile devices, or I'm going to a mountain for skiing, right? I need to basically be able to use it, or a ship in the middle of an ocean, any kind of these environments. So they are uniquely positioned for computations where you don't need to go to the cloud to get things done. It's as simple as that. So SLMs are a perfect fit for that. Second is, I may or may not have a resource constraint, but I have an application which requires me to do at scale computations, preferably at a very low latency. So these fall in the bucket or category of low latency execution capabilities, where basically use cases like where I may need to make like millions of calls, but then I need to be able to make intelligent based routing in some way, which is then coupled with a very fast response times. So these are more towards the, you might say these are the kind of devices I'm looking to run these models on, which has or which requires, let's say, owing to certain regulatory compliance, organizational requirement, or edge devices, lower cost of execution. And also, I may not have an access to a massive number of specialist GPUs. So they are combined into one category of use cases. So these could be specific tasks, as you see, can be improved performance via fine-tuning large model out of the versus a large model out of the box. So all use cases that fit in for these kind, are perfect for SLM. So let's take an example. Let's say, because SLMs can work offline, let's say more people will be able to use AI to work in ways that haven't been done in the past. I mean, so let's say basically you see an apple farm, right? Let's say someplace in south of Kashmir. Consider a farmer basically walking in, inspecting crops, and he sees that I see some kinds of a disease on a leaf of a branch, basically. So usually this kind of affects apple farms quite a lot. So is that what you see on the right now on the screen? Is called a leaf miner disease. In the past, we used to have those MCCM, we used to call it multi-scale feature extraction method of kind of taking a photo, passing it on, doing multi-layer study, and then coming up with all of that can be replaced right now with a transformer model, decoder only basically variant, which is technically what your SLM is. And it can give you instant visual capability. You can just take an image, put it in the SLM, directly run it, and says, what, I see this. At what stage is this? What kind of a disease is this? Is it at all a disease or not? What are the protective, measures I can take, and can get immediate, recommendations on how to treat these pests or disease in this case, right? No need to kind of go back and do the offline loading. This is like one of the use cases you can do, or SLMs we are seeing people, cater to or use for. Let's quickly cover some specifics of the Microsoft Phi-3 family of SLMs, right? So a few important points in this image, right? This basically, first is, the point to remember is Phi, the entire family of models. When I say Phi, means Phi-3 and 3.5 and onwards. They're a Microsoft research-led program within Microsoft. Secondly, these SLM models are available to you under the MIT license, the open source. Third, the SLMs are not to be thought of as a replacement of LLMs. This is important for me to clear. But SLMs, as we covered earlier, has specific use cases which you would definitely look to use them for. Phi-3 as of now was the gold standard before the release of 3.5 in August, which we will cover soon. But then again, the essence is to basically solve complex tasks, vis-a-vis performance across SLM categories in the industry right now, what you see on the image, right? And the image is very important to understand. You will see this release for 3 and 3.5 also. This, in fact, this simple image is, if I articulate it correctly, is the culmination of the entire research done by our team for making sure that Phi-3 or 3.5 and onwards has the best performance, the quality, vis-a-vis the size of the parameters the models are using. So why is this important? Because X is the size in billions of parameters, and your y-axis represents the model quality, what do you call it, as measured by the performance on the MMLU benchmark. So you can see here the Phi-3 mini with 3.8 billion, which performs better than models, in fact, twice the size. And you see Phi-3 small, 7 billion parameters, and Phi-3 medium, right, 14 billion parameters. Also, perform much better performance. In fact, I'll talk about this in the 3.5 in greater depth. But the point to note here is not just where the competitors like Llama or Mistral or Gemini is placed on the graph, but to basically how we see it is gradient. And we try and understand the slope of the gradient for a family of models. For Phi, you will see it's much steeper. That means technically per parameter, the added advantage to a computing benchmark is much better than the other competitors out there in the market. That's how you should look at this image. Now, to understand this, that why is it so? Why are these Phi-3 models better performant in nature? So we have to kind of take a look at them in let's say the technical specifications and go a little deeper. Now let's spend some time on this, because this is the crux of it, right? If you classify the different models. So 3 mini technically is a 3.8 billion parameter SLM, which has been trained on a 3.3 trillion tokens. Tokens, I'm sure everybody is aware of. It's basically the minimal word unit, right? I mean, you decompose a given English statement, or let's say in English language, and then to the lowest amount of characters at an indivisible unit. That's basically the token. And then we use a specific algorithm called a tokenizer to basically convert them, right, into the, let's say, model or the format in which a particular language model can understand and process it at a very high level. So 3.3 trillion tokens were used for training it. Now, it achieved 68.8% on the MMLU. That is basically at launch, the number which you see 70.9 here, technically was 68.8. So MMLU is basically the massive multitask language understanding, basically a benchmark which is used as a standard, like industry standard, to measure knowledge acquired during the pre-training. This is very important, right? And by evaluating the models exclusively in what we call a zero-shot and a few-shot settings. And this is very important. So it was initially 68.8, but then it got improved. The latest number was 70.9. I have put that. Then there is another type of a benchmark in addition to MMLU, which is again one of the industry standards. It's called MT-Bench, which is basically you have a single turn is a single chat, and you have a multi-turn is a multi-chat. That is the ability of a large language model or a large multimodal model or a small language model to engage in a coherent, informative, and engaging kind of interactions in a multi-turn, chat, let's say, environment. So even the ranking on MT-Bench for Phi-3 mini was pretty high. It was 8.38. Very important is it comes into two variants. So you have the default context length or the window size that we call 4K tokens, and we have the extended or the long, context length, which is supported as of now, it's 128K tokens. So that's basically the mini. Now the small, is we have scaled from 3.8 to 7 billion parameters, trained on again 4.8 trillion tokens, and it basically had 75.7% at launch on MMLU and 8.7 as you see on MT Bench. Again, comes with the default context sizes. So you have the 8K, and please note the difference between the 3 and small. So if you have a requirement of where the default context length you would like to use higher than that of 4K, then you should stick to Phi-3 small, because the starting is 8K, but you can scale it up to 128K. So the point of observation is the long context length. Basically, we use a strategy called rope to kind of make the context length longer. Is the same for the mini and small, but smalls default is higher than that of mini. Now coming to medium, right? Medium has a 14 billion parameter SLM, trained on, again, if you see the same size of tokens for the small, that's again 4.8. It's the same number of tokens on which it was trained on, right? Which means technically what this means, it means that the Phi-3 on the screen and Phi-3 medium SLs are trained on the same number of token, but Phi-3 medium, because a lot of post, let's say, training optimizations that we do, in fact, it has a higher in MMLU benchmark and MT benchmark numbers. It's 78.0 on MMLU and 8.9, which is pretty good on the MT benchmark. So technically, this means that comparing across all the three models, if we do at a very high level, mini, small, and medium, it's basically medium is the highest results, I would say, in terms of both MMLU and MT benchmark. And they, again, are available in two variants right now: default context length, which is 4K, and the long context length of 128K. This is same as that of the mini and the small. And finally, 3 had a cutting edge and a very multimodal model, which is referred to as the Phi-3 vision model. That's based on the Phi-3 mini. This is very important to understand, and is a 4.2 billion parameter multimodal model. So what does that mean? Technically, it means that I can integrate information from diverse sources here, basically, such as text input, audio input, video input, multimodal model. Then I can build a much richer and a much more complete understanding of the contextual scenario of the underlying data, which mini, small, and medium lacks. And very important is, in summary, at a very high level, 3 vision was and still is a model which is in use, which is basically designed to process an image and a textual prompt as an input, and then subsequently generate textual output. So this model, again, without going into the details, if you open up the technical report and read it, Microsoft has a very detailed technical report for the Phi-3 family. The base underlying architecture is basically a combination of image encoder and a transformer decoder only block. The same holds for just the transformer decoder only block, holds for mini, small, and medium. But Phi-3 vision, it changes a little bit. It's basically a combination of the image encoder plus the transformer decoder only block. It is great for tasks like whatever requires reasoning over image and text together. So let's say OCR or a Q&A over extracted text, or let's say you have a chart or a diagram or table understanding. We'll take a look at all of these in the demo section, right? You should then, for these use cases, you should use the Phi-3 vision instead of the mini, small, and medium. So this is an important aspect. Now coming to the 3.5 for us to understand. August 2020.
Hi,
Yes, please.
Subhasish.
Yes, please.
Yeah, just on the MT bench, can you please explain what you mean by MT bench, where it is actually measured, actually, MMLU and MT bench?
Yeah. So basically, see, there are a host of academic benchmarks that the industry has. And whenever any new model comes out, you will see always it comes associated with a host, loads of like benchmarks. Now, these benchmarks are nothing but different tests which has been performed on the foundation model. And then maybe when the model comes out and it's again tuned, right? Specifically, those are the updated numbers every OEM kind of comes up with. Now, in that categorization of tests, you will find they come in buckets. So some are human logical reasoning. You have a range of tests. You have for chat capability. How well is the model able to understand human inputs? at a 0 shot
Okay.
or a few shot setting and then kind of give an output. So that is the empty bench is what is one of the most standard, let's say, industry favored benchmark for this particular use case. Then you have specifically for English language, specifically for multilingual languages, specifically for mathematics. There's a host of tests that are there. In any other reports, you will find there's a bunch of tests. Around 25 to 30 tests come out of which empty bench is, just to remember, it basically measures at a very high level the ability of an LLM or a multimodal model, that is MLLM or a SLM, to first engage in a coherent, then informative and understanding of a multi-turn chat. That means it's not a single chat where I ask, let's say, what is the capital of France? It's a single chat. It's Paris, then the chat kind of ends. But a situation where, for example, I ask, could you explain me the weather today, let's say in a particular city, and is it going to rain? Absolutely. So it is a very logical, contextual conversation, very important. Or even in the first chat, if I just say that what is the capital of France, instead of that, if I say for empty bench, it would be, I am planning to travel to Paris. Would you help me understand a common itinerary which maybe Asian tourist follows there? And what is the weather gonna be like? That's the third point. Let's say chat if I put. So the model technically, if it's highly trained on very good curated data, will be able to first contextualize that this person, because this conversation is still going, is not talking about going to Tamil Nadu. He's talking about going to Paris. Still, my conversation is in link, right? So it's a multi-turn chat. And if you then train it, so empty bench has added advantages to it. You can even train it on a few short level of trainings, right? So the composition, not going into the details, is basically the empty bench. Now, that is one of the industry standards.
Okay, got it.
Now going to 3.5, now 22nd, I think August, that's 25 days back, Microsoft released the 3.5. So let's quickly understand at a very high level what's special about 3.5. Very, very, very important, multilingual. This had been a common request for multiple, let's say, segment of customers. I have had the opportunity of interacting with. They had told, what, I would love to use whatever use cases you mentioned in SLM, but I would love to use it for Hungarian or Italian or Arabic. Do you have that? The answer was no before 3.5. Right now, the answer is yes, because 3.5 is multilingual. 3.8 billion parameters you're going to take a look at is basically the scale law starts from there. So just remember that. Default context length. And again, all of these have using rope strategy or extended context length. Basically uses in the underneath, if someone asks what's the architecture, it's basically a transform architecture, but instead of just using an encoder decoder, or an encoder only, we are using only the decoder only transformer block. By the way, I have a slide later just to at a very high level, explain this. Release date was August, and what are the supported languages? So as you see, you have Arabic to Chinese, Czech, Danish. I'm not going through a list. Japanese, Korean, Spanish, Swedish, all of these different languages. Also, it has been trained on. That means the curated data we use for pre-training, training, and the post optimizations also includes multilingual, support of the languages. So that's what 3.5, is catered to. Let's spend some time on this slide, which we saw an earlier version on. And here I have marked it on a red slope gradient and the black. Is in X, again, what are we tracking? It's basically the billions of parameters, and Y-axis basically gives us the model quality as measured again by what? The industry says you should take a look at immediately the massive multitask language understanding, the MLU benchmark. Again, this is a global standard, how when a model comes out, they're rated like this. That is basically your billions of parameters versus how good is the performance. Now here, you need to stop and take a look at the other different models also there on the screen. And why is there so much buzz in the market? That's understood by this particular image and a very high level. Is if you see the 3.5 mini, which has 3.8 billion parameters, right? Which performs better than models twice its size. And if you see the other models also there on the screen, the mentioned, right? The point to note is not where exactly they are placed, but how we look at it is these scaling laws are applicable to this particular image. Now, how do you understand that? So very important is to, if you observe the red line here, right? It's basically the steep of the gradient that you should take a look at. Now, if you see the rest of the models on the screen, right? You have the Mistral, the Gemmas, the Llamas, right? If you observe the black line there, for example, right? So the point to observe here is in the black line, there's a very linear, that is a predictable increase in the MMLU benchmarks. That is one of the characteristics of the large models. That means, what this technically in English language it means is, if I build a largest model where I throw in from a billion to a dozen of billion to a multi-billion to a trillion parameter, and then of course use equivalent amount of resources to train it and pre-train, train, and then do optimizations post the training, I will get a linear level of performance. So that's referred to as a standard scaling law. But now, quickly, if you come and take a look at the Phi 3.5 model shown on the screen here, you will see the red line is very opposite. The focus point here is the slope of that particular gradient. Now, you will see here, if the slope is smaller, that means it is growing slower, which in case of the larger models, correct? Which basically means that per parameter I add to a larger model, the performance output is better. The scaling laws are better. Now, this is because of the highly curated data that we use for pre-training, the training, and very, very important, the two kinds of post-training optimizations that the Phi 3.5 models use. For folks who are interested, so basically, if you see the red line is much steeper, that means per parameter I add, the performance is exponentially better than the ones which we are seeing in the larger models. How does this happen? The secret of this, basically, it's not able to, folks cannot understand is deeper from this image. For that, you need to be able to read the technical report. That report has post-training optimizations, a section. It talks about two important things. One is the SFT, the supervised fine-tuning, which the Phi-3 models go through after having, of course, pre-trained on highly curated data set, right? And then also the industry standard that we have seen is they use something called a PPO, that is a proximal policy optimization. Phi-3 models are not using it. We have chosen to use DPO instead of PPO. Again, it's explained there in the technical paper. So DPO is basically direct preference optimization, correct? So that also is one of the fundamental reasons why, at a summary, your standard scaling law applies definitely, but the performance output of the Phi-3 models is much better, in terms at times exponentially better than the scaling laws observed by the other set of industry models. That's how you should look at this image from. This is an important point. When you look at an image like this, you should also see the gradient and the slope of the gradient. So this is the key takeaway. Now, again, at a very high level, at technical specifications level, what are they? This is important to understand. So again, parameter wise, it's you have, so what we did from 3 to 3.5, major change, if you see on the screen, 3 was basically a series of 4 models. We have kind of combined and made it basically lessen the number. It's basically then mini, vision, and a new introduction to the family called MOE, the mixture of experts. You'll understand what that is. So in mini, it's basically, it's a 3.82 billion parameter model. And we have kind of, it has, of course, it has undergone, pre-training using a multilingual combination of synthetic and high quality filtered data. This is very important. This is one of the fundamental reasons why Phi-3s are so good performant. And it has been trained on 3.4 trillion tokens, around 24 plus languages were included in the training tokens, very important. Post-training SFT, PPO, and DPO. And DPO is the preferred choice for the Phi-3 models. So this again, and what are these processes include at this level the training optimization? If you have to understand, it's basically a combination of human labeled, synthetic, and translated data sets. It's a certain degree in which all three of them are used. Points to note here is that Phi-3 Mini shows significant improvement on Phi-3 Mini on multilingual support. So Phi-3 Mini was none, right? So Arabic, Dutch, Finnish, Polish, Thai, Ukrainian, they received a great boost from the new Phi version with 25 to around 50% improvement in performance. So this is very important. So to put this in context correctly, you should look at it in this thought that the Phi 3.5 mini that you see on the screen right now, it shows very good performance, like top performance for any sub 8 billion parameter model in English as well as several languages. It is very important to note. And for multilingual knowledge intense tasks, the recommendation is to ensure you use Phi 3.5 mini, but not as it is, but using the model in a RAG setup, retrieval augmented generation setup. Again, comes with a MMLU number and comes with a default context length 4K, and you have the long context length using rope, that is 128K tokens. Phi-3 vision, this is what we call specializes in, of course, whatever work 3.5 does, 3.5 vision can also do, but it is mainly targeted for solving, that we'll see in the live demo, is what we call text VQA and science VQA type of tasks. What does that mean? That's basically text visual question answering. That means I have a text, an image in which some text is image in which some text is thrown. You want to understand that, extract that, read and ask contextual relevant question to that text embedded in an image. That's basically text VQA. And the same of that, but in a much more complex engineering, science, research, biology, laboratory setups are these science VQA. That's basically science visual question answering. We'll also take a look at that in the demo. This will be easily understood there. So it often involves multimodal reasoning, which is the core strength of Phi 3.5 vision. So this is an important point to understand. And 3.5 MOE. Now, what is this all about? This is a new entrant, or in addition to the 3 and 3.5 model family. So what it does, it basically comprises 16 experts, each containing around 3.8 billion parameters. And one important point or question is, recently one of my, let's say, acquaintances asked me a good question that, I'm hearing this Phi 3.5 MOE. What is this E in the MOE, this expert? Is it a human being or a translator or a machine? This is a good question. So expert refers to you have to think about if the entire model is a neural network. So a sub or a specialized sub network within the larger neural network, which is designed and trained to handle a specific task or part of the input data or tasks, is basically defined as an expert. So MOE model, or the Phi 3.5 MOE, is basically built on the capability of these 16 highly trained, highly specialized subnetworks doing certain aspects or inputs of their tasks. So these are the 16 experts layers to this. And each layer contains around 41.9 billion parameters, with a total model size of 42 billion parameter, but it activates, you have to remember, 6.6 billion parameter when using 2 experts trained on, again, a 4.9 trillion tokens. Very important, again, supports 20 plus languages. It basically, as you see here, MOE, and there's a vast difference between the mini and the vision, is because instead of PPO, again, we are doing SFT plus DPO, which is the direct preference optimization, utilizing both, again, human labeled and synthetic data sets. Default context length is, again, 4K, and long using rope is 128K. So this is at a very high level what the 3.5 family is, and some of the details around it, right? Again, not going into too much depth of performance comparison, because at a very high level, if I compare, or I take the 3.5 MOE, the mixture of experts, which is a 42 billion parameter MOE with 6.6 billion activated during generation, if you see, beats Llama 3.18 billion handsomely across the benchmarks. And in fact, at a very high level, you can think of this as that the MOE outperforms much larger or bigger, like multi-billion and trillion parameter models in reasoning capability, which is very important. Now, if you see the different capability, tasks in which they're tested, and it's only behind GPT-4o mini for a few tasks. If you want a greater kind of a comparison on different type of performance, type of reasoning, type of tests, all of this is in detail in the technical paper, which is for the 3 family, as well as if you go to Hugging Face, also each of these models have a very detailed kind of contextual study of how it performs with the different competitors. I've given the 3 links also. You have a Microsoft Phi 3.5 mini instruct, an MOE instruct, and a vision instruct. You can directly go and download those papers and read them. Those are basically links explaining how they perform across different performance parameters. And we will spend rather some time on the demos. So architecture at a very high level to understand. This is for your contextual understanding of what is happening in an SLM underneath. Something is happening, right? That's why you are getting all these outputs. I can definitely do a pre-training, and do a post-training optimization. But what's the fundamental from a transformer's point of view? So going to, again, brevity of time, will not go into depth into transformer, But it is important to know that, for an LLM or an SLM perspective, like, because very simply put, a transformer model is technically what we call a sequence to sequence model. All SLM models are sequence to sequence models, right? So there are three variants to this model. Now, this is important to understand. So this is basically how the manner in which they are created, and the manner in which the underlying transformer model is using what we call the multi-head attention layer. So the original 2017 white paper from Google, that is, if you have kind of had the chance ever to take a look at or read it, Attention is All You Need by 𝗦𝗲𝗎 et al., right? That basically talks about the classic encoder decoder architecture, right? Google BERT had that. But it's very limited because you have very strong regularization, what we call, between the layers. So there is very less freedom. So there is very less ability to create new content. That's why it was very restricted. Decoder block only, it has the least structure amongst the three, popularized, of course, by the famous ChatGPT. Again, Phi-3 family of models, from the context of Phi-3, because we are discussing SLMs, is a decoder only transformer block, architecture. Just remember that. So ideally what transformer does is it takes a sequence as an input, where a sequence element input has basically elements, right? Like words or images. So on our slide, a sentence, let's say I've taken, is tokenized into an encoding scheme with a fixed number of integers. And then the dominant paradigm right now in AI research is I represent each of the sequence, element as a dense vector, what we call it, because we technically need to multiply them. So we technically arrive at a what we call sequence of vectors or sequence of dense vectors. And then what we technically need to do is basically do a interaction, or a model the interaction between the sequence elements. So, and how the transform models work, if you have a generic idea, is basically we arrive to a step where we do a probabilistic distribution of the most contextually relevant vector. So, and the transform models basically, is a kind of an SLM that technically uses a combination of two things. So I have a multi-head attention, and I have to model this interaction between the sequence elements, correct? And very important is the FFN, we call it, the feed forward network, which is also part of every LLM and SLM, right? So again, here, for example, you see the decoder only block. Now, very important point is, this is right now what I explained is how all transformer models work. Is I have an input sequence, I encode it, I take that dense vector, then I do a probabilistic distribution of the most contextually relevant vector at a very high level. Now, what happens in an Phi-3 kind of a decoder only block is, again, I do the same, but there are three important stuff that happens here. These are part of the three what we call design features. First step is you concatenate the input and target. Then second is you apply the same set of parameters to both input and target sequence. And then basically we use the self-attention, which also serves as the role of cross-attention. Because if you see these lines, like these basically crisscross lines, which play a vital role, right? So these basically, also, play the same role. So the self-attention basically plays the same role as the cross-attention. This is very important. And then you have an output sequence. So this is technically how let's say an SLM works. So basically now I have come to an end to what we had from a presentation perspective. Let me, kind of